So, welcome to episode 9 of our story, and we talked about the character of light itself or properties of light itself, and then we were talking of Planck radiation law, another hero of our story, Max Planck. And the idea was that if you have radiation, electromagnetic radiation, which is in equilibrium with some enclosure at temperature T, how the energy is distributed in different wavelengths, because it will have different wavelengths. So how much energy is in this wavelength, how much energy in that wavelength, etc. So that distribution that Planck obtained, and I discussed a little bit of that assumption of each oscillating material in the wall absorbing energy and emitting energy, which was proportional to or integral multiple of some constant h times the frequency with which it oscillates. So that material oscillator in the wall and this radiation, they are in equilibrium with each other, transferring energy into each other. So from there, Planck did all those calculations and got that radiation formula. The description was not the actual path on which Planck got that. It's a kind of an equivalent description. In fact, during 2 years, 1898 to 1900, Planck wrote 4 or 5 papers on this, each time modifying his approach, each time doing something new there, and finally he gets it in this particular fashion. Alright, so the final derivation of Planck in this uses extensively thermodynamics, right? Thermodynamics. He puts some material oscillators, not necessarily in the wall, in the middle also, in the radiation also, which can just exchange energy, and then he does a lot of thermodynamics there. Why I am focusing or mentioning this thermodynamics thing so forcefully, that our next and very, very important discussion will be on Einstein's 1905 paper on photoelectric effect, which earned him the Nobel Prize in Physics 1921. And there too, he talks of a lot of thermodynamics of radiation and oscillators. So let me talk a little bit about what that central thing is, which Planck is using, which Einstein is using, and many others are using. So thermodynamics is a description of behavior of system having large number of entities. Like a gas in a chamber, you have some 10 to the power 24 molecules and all that. So Newton's description of F equal to ma will not be useful there. So how to handle those kind of systems, for that this thermodynamics is developed, and then there are laws, first law, second law, third law and all that. So the first law is that for an isolated system, the energy is constant. System can change its configuration, but the energy will remain the same unless you are supplying energy or taking energy away from outside. So that's first law, fine. Second law is more important for our discussion. And what is second law? This, in fact, is more interesting than the first law. And that is, let me give an example. Suppose I have water in one container. Suppose I have water in one container and some water here, and then this is at some 20 degrees Celsius. You have another container, and that this also had some water, so let's say same quantity, but the temperature is higher. Let us say it is 60 degrees Celsius. Okay, assume isolated system from surrounding. We are not allowing time to interact, or we can put it in some enclosure and so on. So whatever is this is the system, this plus, and no interaction from outside. What we do? We take a bigger container. And just put all this water into this and leave it. So we pour this water and then we pour this water and then we leave it. So we have a larger amount of water, the entire water here, and that will be at some temperature, the amount it's saying, it will be 40 degrees Celsius. So from this system, just by mixing, right? We have not done much on the system. We have just mixed it, and it can reach to this system. So it goes from this configuration or this situation to this situation. Can I invert the arrow? Is it possible that I take this container, this water, put half of water here, half of water here? This takes the temperature 60 degrees, this takes the temperature 20 degrees. Can the process be reversed? I had not put any refrigerator or any boiler to increase the temperature, to decrease the temperature. I just mixed it. Reversed, I separated. The energy is same. But this is not possible. This is possible. This is not possible. So there are processes which can go only in one direction. If I rub my two hands, right, they become warm. Okay, they become warm. And then what happens? This kinetic energy of my hand is getting converted into thermal energy. Right? Now what I want to reverse it, the thermal energy goes down, my hands cool down, and that energy is converted into the kinetic energy. So my hands again start rubbing to each other by their own. Because now the thermal energy should be converted into kinetic. I don't have to work. Okay? In the first process, I gave kinetic energy, and then that kinetic energy was converted into thermal energy. It got hot. I want reverse. I won't work now. This thermal energy, that will itself be converted into kinetic energy, and my hand will start moving. Will it do? It won't. So processes, most of the time, there are processes, of course there are some processes which can be reversed, fine. But there are a number of processes which can move only in one direction. The reverse is not possible, even if the energy of these two systems are, these two configurations, or in these two situations, the energy is same but still. So this is the area of second law of thermodynamics. Second law will decide which is possible, which direction is possible, and which direction is not possible. And for that, they have to construct a function in each configuration, and that function is known as entropy. So entropy of this system, one can calculate entropy of this system. What entropy is, maybe I will tell just one or two sentences on that, but there is some function of entropy. So in this situation, you calculate how much is the total entropy. And then in this situation, you calculate how much is the total entropy. And the law is the entropy cannot decrease. The total entropy of an isolated system cannot decrease. It has to increase, or at best it can remain same. So if it remains same, then yes, the reversal is possible. But if it increases, it cannot go back, because entropy of an isolated system cannot decrease. Okay, so once you know how to calculate entropy, then you can say that, okay, fine, can it go this side to this side or this side to that side? So that entropy is very, very crucial. Now, what the entropy is, that also we can talk a little bit. Entropy is generally said to be related to randomness. If randomness is more, entropy is more. If randomness is less, entropy is less. Or in other way, if you have a system, let's say gas here. Let us say a gas here, and in that gas you have air in the room, and here you have put some fragrance vaporizer, so that this spreads. You put it here at certain time, and then it spreads. Okay. Now, if you think of one situation where your fragrance is here, this whole thing is air, but that particular material which gives you that flavor, that good smell, that is confined to here to start with. In this configuration, I want entropy. And then another configuration when this has gone up everywhere in the room. Of course, the air is there. So in this configuration and this configuration, entropy, one can already tell that, okay, this should have larger entropy because this will go here, this will not go here. Once it has spread everywhere, once it has spread everywhere, can it go back in this situation? All these molecules of that nice material that is confined into it just gets confined into one corner. Will it do? It will not. Entropy here is more, entropy here is less. Now, in this situation, if I see, and I say that, okay, I want microscopic description, all right, in very small volume, I construct very small volume, and then I ask, how many air molecules are here, and how many is this material A? Those molecules are here. How many here? 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 And in how many ways this can distribute, given this situation. Now you have to distribute these things only in this much of volume, whereas air can distribute here and here and here everywhere. So here these many molecules, here these many molecules, here these many molecules, here these many molecules, here these many molecules. See how many ways you can get this. Okay, in how many ways you can get this? Count that. And in how many ways you can do this? Count this. Here you have much larger number available. In many more ways this can be achieved. But here it is confined. It's confined. Oh, you have to put everything here, and then the rest is only air. But if you allow this to spread, then you can say, okay, there are 5 molecules of this material here, and 7 here, and 3 here, and 4 here, and those numbers can change in different ways you can generate from there. So more number of ways a particular situation, macroscopic situation, can be obtained, larger will be the entropy. So that entropy is something which Planck calculated. If you have a radiation in a chamber, and then you have these oscillators, and then oscillators can oscillate in different frequencies, and each frequency you can divide energy, that okay, this much energy here, this much energy there, this much energy there. For this frequency, oscillators of this frequency, this much of energy, oscillators of those frequency, that much of energy, and so on. And then you make a count in how many ways you can distribute. From there they calculate entropy, and then from the expression of entropy in terms of whatever energy, whatever, so from that expression they do mathematics and get that radiation formula. So that is say one final way, but the basic thing is still there. Still radiation and those oscillators, when they exchange energy, Depending on what is the frequency of that oscillator, the exchange will be only in integral multiples of h times frequency. So that thing will still be there, but this process of going through entropy and thermodynamic considerations and expressions, and from there getting the final distribution, that is a very, very important tool or path for our discussion. And very interestingly, our scientist Satyendranath Bose, he also worked on this. He also derived that Planck's radiation formula in 1924. And that story is very, very inspiring in the sense that he made this derivation purely without any oscillator or material particle or anything classical, anything with the existing one. In Planck's derivations, somewhere this discrete energy hypothesis is added to the classical physics. Whatever is there in classical physics, it is still there. He is still using classical physics. And on top of that, he is putting an extra element that the energy exchange is proportional to h times nu. But what Satyendranath Bose does, he does away with all those classical considerations, and with very purely, you consider a gas of pure photons, nothing, no oscillator, nothing. Okay, and then do this entropy calculation, and from there he derived his Planck's radiation formula, and then he sent this to Philosophical Magazine. They rejected. Then he sent it as a letter to Albert Einstein, and Albert Einstein read that, and the request of S.N. Bose was that if you think it is worthwhile, then you send it to some journal, some German journal, Z Physics. And Einstein could understand the significance of that. Einstein translated that English version of S.N. Bose into German, got it published in 1924, and from there Einstein writes in that communication note that it's very significant and I will work on these ideas. And Einstein worked on those ideas, and then that new branch is known as Bose-Einstein statistics. And all the particles which follow that path, that distribution or that physics, are known as bosons. Right? You have two varieties of particles, fermions and bosons. So this bosons, that Bose is our own Satyendranath Bose. So with this Planck's radiation law, we also have some emotional attachment. Now we are ready to discuss Albert Einstein's paper of 1905 on photoelectric effect. Actually, it is not on photoelectric effect as such. Although that paper, that part where he discusses photoelectric effect, that plays instrumental role in getting him Nobel Prize 1921. But the main paper is again on the thermodynamics of this radiation. And in that, he establishes that independent of the oscillators, although he also works with oscillators and things like that in equilibrium with radiation, but then finally he comes out with the structure of that radiation itself, not only at the time of exchanging energy with the oscillators. The radiation itself, by itself, it is to be seen as separated units, spatially separated, located at different places, small units, and each unit will have some energy. If it is say monochromatic radiation and the frequency is nu, then each unit will have frequency h nu. Just h nu, not double of that, not triple of that. It's not n times h nu. Each unit has It's new energy, and such units are floating here and there in the cell. That is what makes electromagnetic radiation. And if it is a combination of different frequencies, fine. The component with frequency nu, if you look at that only, that will consist of, once again, these small separate packets, separate units, each having the energy h times nu. So that is how this theory is taken ahead by Einstein, and then that theory, that structure of electromagnetic radiation, that explains photoelectric effect observations very well. So that we will take up in our next episode.